All right, so we want to start with electrostatics. We do electricity and then do electronics, right? All three E's, past papers, then we do some magnets, right? There aren't many magnet questions, right? Or the rest of them, anyway. So, okay. All right, a form of energy resulting from the presence of charged particles, such as electrons or protons, right? Either statically as an accumulation of charge or dynamic current. So all this is saying here, if you have charge that's not moving, that's called static charge or static electricity. If on the other hand, you have charge that's moving, it's called current. Okay? Here, we have the electric fields around two charges. We have the electric fields around a negative charge. It goes towards the negative. Electric fields around the positive, they go away from positive. All right? Unlike charges attract, like charges repel. Just do me a quick favor, right? Draw the electric fields between these two here. So let's round up these animals. All right, so you will see here that like charges attract. Sorry, unlike charges attract. So the electric field will leave the positive and go towards the negative. The one on top, like charges repel. So the electric fields will not interact, right? They will look something like that and move away from each other. Okay, and there's a little region in the middle where there's no electric field. Okay, so you remember the rule, right? All right. The first quantity that we need to learn about is charge. Charge is equal to current by time, right? Why is my pen not working again? What's the SI unit for charge, Pete? What's the SI unit for charge? Coulombs, right? Coulombs. Oh, just give me 1 minute. This thing giving some trouble here. Right. Yeah. Right. So coulombs is the SI unit for charge, and the next SI unit is current per second, amperes per second. That's okay. So we need to remember those two SI units, right? Now, when one thing we need to remember is that we can obtain these static charges via two methods: friction and induction. Sorry about that. So charging by friction, here's what is happening. You might have a rod and you have a piece of cloth. When you rub the cloth on the rod, based on the material, electrons will move. So the electrons, let's say, might go to the rod. If the electrons move to the rod, it means that the cloth will become negative and the rod will become positive. That is called charging by friction, right? It varies based on the rod. Sometimes the rod become negative, sometimes the rod become positive, okay? Charging by induction works like this. If I give you a spare and the spare has no charge, and then you bring something positive next to the spare, what you will do is you will induce a negative charge here. As a result, there'll be a positive charge on the next side, right? That is charging by induction. If you move away the rod, the charge is no longer there on the metal spare. But here, if you move away the rod and the cloth, they both will have the charge for a period of time. That's okay? So you have charging by friction and charging by conduction. Anybody remember what is one good use of what is one advantage or one good use of charging by friction or any kind of charging? Static charge. What's an advantage of a static charge? Oh, I'm going to change the question. When is a static charge useful? Anybody remember? Painting cars, right? Charge the car, charge the paint, and allow a nice even paint all over the car. When is charging bad? Right? When filling gas in your tank, like an aeroplane, for example, while the aeroplane passing through the air, it will develop a charge by friction. So when it lands, because of the aviation fluid close by, you have to make sure it discharges as soon as it lands. Right? And next one is lightning. So those tall buildings. Anybody remember what it is do? So the tall buildings, for it not to be damaged by thunderstorms. You have a lightning rod. What the lightning rod does do? Right. It does two things. It weakens the charge of the electricity, and it also pulls any electricity that any lightning that hits the building from the rod down to earth and neutralizes it. All right. So it has two uses, making it weaker and pulling it down to earth. Okay. Now, if we have a circuit and we have a supply, we would be able to allow the electrons to flow. Right? Once the electrons are flowing or the charge is flowing per unit time, we have current. So that's why current is charge flowing per unit time. What are the four things every circuit will need in order for current to flow? What? A load, battery, a supply. What else? A load. What else? a switch, and connecting wires. Right? Those are the four things every circuit needs. For every circuit, we have to learn these circuit symbols. These are all the circuit symbols here. All right? As a quick practice, just draw this using circuit symbols only. Huh? All right, nice. So you should have something like this. Battery, positive, negative, positive, negative. Switch, connected to a lamp, connected by wires. So it might look something like that, right? Right, quickly. How do we measure current in a circuit? We use a ammeter. How do we measure voltage? Right. Always remember, an ammeter is connected in what? Series, and a voltmeter connected in? All right, nice. So let's take a look at this circuit. And I want to put in an ammeter and a voltmeter in this circuit, right? So I can put the ammeter right here. It don't matter where. Connected in series. But the voltmeter has to go across the load in parallel. Okay? Remember that. How do you know a parallel connection? How you know? How you know a parallel connection? Well, remember current flows from positive to negative, right? So if the current reaches a point and has to choose which direction to move in, it means that those two are parallel. So current will go up here or come down here. Anybody remember why current does not flow in a voltmeter? There's a reason why. Current does not flow through a voltmeter because of a special feature of the voltmeter. High, yeah. The voltmeter has high internal resistance. It has high internal resistance. What about the ammeter? The ammeter has what? Low. Why is it low? The reason it's low is because you want current to flow through it, right? Right? You want current to flow through it. All right, nice. Next thing we need to remember after these symbols, the two types of supply, alternating supply. How we know if a supply is alternating? Besides the up and down, because you could also have this. That is not alternating. Something important. Right? There's always a change in polarity. So positive, negative, positive, negative. If it's varying, but it's still staying positive, then that is called a varying DC. What is still a DC? All right? That'll be a varying DC. Um, here's a direct current, right? Here's a DC and we have a AC. Take a look at series and parallel. And the most important table, write this down. Write that table down there. That's the most important table. All right, sorry about that. Right, so very, very important, right? We have to remember for series circuit, we have to remember current is the same, voltage splits up, and there's the formula for resistance in series. In parallel, current splits up, voltage is the same, resistance given by this. Quickly, I just wanted to remember what each circuit looks like. What we can say about R1 and R2, Carisha. R1 and R2 and R3. R2 and R3 are in what? Parallel. What about R1 and a combination of these two? Series, right? So R1 is in series with a combination of R2 and R3. Okay, nice. As a quick example, here are we doing? Here 10 volts, and each of the R values is 2 ohms. Can you find the total resistance? So use the right resistance formulas. And can you find the total current? Try that fast. And then part 3, we are going to try to work out the current in R2. Try that fast. let's see what the calculation will look like, right? Yeah. So as we said R2. We said R2 and R3 are in parallel. So we have to be able to use the parallel formula there, right? So I'm working out for R2 and R3 first. 1 on R is equal to 1 on 2 plus 1 on 2. So 1 on R is 2 on 2. So when you flip over the R, you will get 1. That's okay? And then we said now to get the total resistance, we said that R1 is in series with the next one bit. So you will get 2 plus 1, which is 3 ohms. Okay? So the final resistance of all 3 of them will be 3 ohms. How do we find current now? We know that V is equal to IR. So I is equal to V on R. So the voltage is 10 and the resistance is 3. All right? So it's 10 on 3 amperes is current. I asked one little question, right? What would happen? What will happen to the current when it reaches here? When the current reaches here earlier, when the 10 over 3 amperes reaches at that junction, what will happen to it? It was split up, right? Very good. And if the resistance are equal, how will it split up? Equally. Okay? So if the resistance, how the resistance R2 and R3 is equal, that 10 over 3 amperes will split up equally. 10 over 6, 10 over 6. All right? So sometimes it really is a place to work out. All right, nice. Let's go back to where we were. Right. Sometimes they like to ask us, find the IV characteristics or draw the IV characteristics of a conductor or a resistor or so on, right? This is the circuit that will always work, right? You have your voltmeter in parallel, your ammeter in series, you have your variable resistor so that you'll get different current readings. You have your supply and you have your load, right? If you want a filament lamp, you leave the filament lamp in the middle. If you want a conductor, you put a conductor. If you want a diode, you put diode, right? But every time you see IV characteristics, this is the circuit. This is the circuit that you run through. Right, this is the circuit that we're going through. All right, nice. By the way, anybody remember what the IV graph for diode looks like? It will conduct in one direction, in the next direction, a real small value. Okay? Okay, so basically it's nothing in the next direction. It conducts in one direction only. Right? These are all the formulae that you need to know. Right? Make a note of it in case you work out some. You might need it, right? V equals to IR, P equals to IV, power loss, and so on. Add them to your list of formulae. Right? Those are all the relationship between the remaining quantities, right? right? Please note that if they say power loss, they can only use the one with resistance in it, right? Okay, nice. Please remember that this W is what? What is called a W? Huh? That W is electrical energy. This P is electrical power. Right? Remember the SI unit for energy, joules, power is watts, right? All right, next thing. Next thing that we need to remember in electricity, we need to remember how to pay bills. Paying bills quite simple, right? Just remember that 1 unit is the amount of kilowatts used in an hour. So for example, if you have a bulb and the bulb has a rating of, let's say, 5 kilowatts, how much energy is used after 1 day? How much energy is used, or how much units is used after 1 day? Well, number one, write down the power and write down how long you're using it for. The power is 5 kilowatts and the time is how much hours? 1 day is 24 hours. So we end up with 120 kilowatt hour. Okay? And then you have to figure out how much 1 unit will cost, and so on, right? Right? So sometimes 1 unit costs 25 cents and you have to work out for the number of units and so on, right? Next thing we have to remember is a diode. And what does a diode do? A diode allows you to conduct current in one direction only, right? When it forward bias, current will flow. Look at it there. How is no forward bias? Reverse bias means no current will flow. How is no forward bias? Huh? Right? You will know forward bias if the current direction is the same as the arrowhead. Right? If the current direction is opposite to the arrowhead, then you have reverse bias and no current will flow. Okay? So as I said, the diode only allows current to flow in one direction only. And as a result, we can use the diode to do something called half-wave rectification. Half-wave rectification, simple. Only one cycle will conduct. Right? So in this example, all the positive cycles conducted, negative cycles, you'll recognize they are not there. Okay? So those are the things that we need to learn for electricity. Next thing is electronics. You have to learn your gates. AND gate, OR gate, NAND gate, NOR gate, right? Of course, you got to learn everything. Just remember this. For the AND gate, 2 ones is give you a 1. For the OR gate, once you have a 1, you're going to get a 1. Right? NAND gate, opposite to the AND, NOR, opposite to the OR. Oh, and they're missing in NOT gate, sorry. NOT gate is what? 1 input, right? 1 line going in. 1 will give you 0, 0 will give you 1. Okay? So those are the gates. You have to learn the NOT, the AND, and the OR. You can figure out the others. Right? The NAND, the output is opposite to the AND. The NOR, the output is opposite to the OR. All right? Yeah. So once you have the gates, let's go straight into some questions. Right, there aren't many magnets, so we'll focus mainly on electricity. All field that might come. Everywhere, you know, no? Yeah, my God, my God. I don't know. What you gonna do? Right? Let's see Shannon there, will you? Shannon, you there? Shannon. Man, to be paying attention to all, boy. All right. Let's try this electrostatics. There aren't many electrostatics, right? Electric field. What's the definition? The region around an electric charge where a force is experienced, right? Write it down. Don't go back to the summary, just write it down. Shannon never there, boy. The electric field is a region around an electric charge where an electric force is experienced. Region around an electric charge where an electric field is experienced. Okay, next. Diagram 8 shows a positively charged sphere, which is attached to a metal insulated stand. Draw arrows to show the pattern and direction of the electric field in the region around the sphere. So if you have a positive charge, electric fields move where? Away. Just try and draw them nice and uniform, right? Because it's a nice circle sphere. Right? Draw the electric fields moving away. All right, next part. Next part. A smaller uncharged metal sphere Q is suspended by a cotton thread and brought close to the positively charged sphere, as shown in figure 9. Yeah, what to do? Oh, sorry. Draw the distribution of charge on sphere Q. What would happen earlier? One side becomes negative, one side becomes positive. Right? On the same diagram, just draw a sphere next to it. No? Next to the first diagram, we should draw a sphere next to it. Atelier, why are the phone? Question right here, Atelier. You have to go on your phone. You want Carisha. Carisha, come on, sit down here now. And then last part. An earth wire was briefly brought into contact with sphere Q, as shown in figure 10, and then removed. Describe what will happen. So think about what it does. What does the earth do? What does the earth do? Pull all the, right, so it will pull all the negative charges away and then do what? It will neutralize it, right? And it will make the sphere fully. So the sphere will no longer have negative. The sphere will be positively charged. And if the sphere positively charged, sphere Q, what will happen? What might happen here? It would move away. It will repel. Are you okay with that? So the battery, sorry, not the battery, the Earth will pull all the excess electrons out of the sphere, leaving the sphere with a final positive charge. And then because sphere Q is positive, it will move away slightly from the largest sphere. Are you okay with that? Yeah. Let's do a small calculation now. Try this here. Real easy. Highest time charge. The guy was eating KFC while class was going on. Yeah. Highest time charge. There's one person mother I have. Number I have was. Tell me quick. Ooh. KFC doing wonders, boy. Nice. Q is equal to IT. I is how much? 11. And T is? Is it sure as hours? Probably be in seconds. If it was eating KFC, I know it would have been seconds. So it would be 8 by 6. Right? 60 minutes to 60 seconds. How much is that? Anybody else? Anybody else? How much? 300 and 800. Very good. All right, so that is your charge. And now find the resistance. Calculate the resistance of the battery given that the voltage was 210. How you finding resistance here, Faraj? And they give you voltage. Oh, Raj there too. Raj hiding in the back there. Boy. Raj, next one is yours, Raj. Raj, come here. R is equal to what? You have voltage. Check back a list of formulas and just write it down. Or you didn't write it down. You have it? What will? Who is it, you know? Right? R is how much? Anybody? R is what? P over I. Resistance, I want to small talk. Just take it on one second, right? So that's 220 over 11, which is 20 ohms. All right? Let's go again. Everybody okay there? Yeah, so you have to remember those little formulae, right? Where do we go next? Are we done? Oh yeah, we're done with that here. That was Jan 2023, right? Let's go again. After Jan 2023, we normally do 22. Where is that? Oh, this is June 2022. Sorry. I'm not saying the Jan. Right, do June 2022, please. It's in the group, so you don't have to wait on me. Hurry up. June 2022. Let me pick on somebody online here. Hi, Charan. Some answers now, please. You and Shannon. Try this. Look back at your summary. Look for these symbols. Work it out. Open the paper on the group and finish out the rest. I correct it all at once, right? Hurry up. out the Wi-Fi and thing. Yeah, real time. Yeah. Most likely, yeah. Not there. Go downstairs and use the bathroom. All right, first one, filament lamp. Filament lamp look like that, right? What is called that? Semiconductor, diode. The fuse looks like this. All right, that's the fuse. What's the next one? AC supply. Why have a blank? Oh, the cell's supposed to be here. Yeah, that makes sense. Right? So you have a cell. A cell is just one alone, right? And the one underneath is what? Huh? Variable resistor. Variable resistor. Right? It's not fixed resistor, right? Fixed resistors don't have the arrows in them. All right, next. Let's continue. They gave you charge and they gave you current. So they want you to get time. We know that Q is equal to IT. So time is equal to Q over I. Q is equal to 9600, right? I is equal to, how much is that? 12,000 seconds. And then calculate voltage. Voltage is what? Voltage is what? IR, but they give it power. So you have to use P is equal to IV. Okay? So power is equal to, voltage equal to power and current. Power is equal to 4.4. Current is equal to 0.8. How much is that? 5.5. Next one. Find the work done. Find work done. Work done is what? Q by V, power by time. One of them can work, right? Q was 96,100. And what was V again? 5.5. B, right? B was 5.5. How much is that? 52,800. Right? Or you could do what? Or you could even use power by time. Right? Anyone can work. Supposed to get the same answer. Same answer. Let's go again. Right? One of these years have two questions. Try this here. Pull out the table. Pull out the table there, right? Good job, Harry Charan. All right, let's run through this fast. Changes 0 to 1. What gate is that? I'll tell you. The first one is the NOT gate and how you join NOT gate. Next one is what? Next one is the, I'll tell you, what's the next one? Next one is the AND gate. How does it look? Two lines, straight curve. What's the summary for the AND gate? Two ones will give you. One on top is NOT gate here. No, remember I told you one was missing. Right? OR gate is what? OR gate is once you have a 1, you'll get a 0. NAND gate looks like this. What are you saying? The first one could be a NOR gate. That's what I mean. The reason I mightn't go with that for the first one is because actually a NOR could work for the first one too, you know. Because a 0 giving you a 1. NOR could work for the first one. 0 giving you a 1. You must have a 0 to get a 1. So a NOR could even work there. All right, let's go again. With the aid of a circuit diagram, describe how an alternating can be half-wave rectified. So remember I showed you this a while ago? You have an alternating supply. What do you need again? What do you need again? What will do this for you? A semiconductor diode, right? Karisha? What does the semiconductor diode do again? I told you about 10 minutes ago. Karisha? What does the semiconductor diode do? I need to pay attention, come for the phone, right? Right? A semiconductor diode allows current to flow in one direction only, right? So you connect the diode, you connect a little resistor, and you put a voltmeter around it, right? The voltage will look like this. What does the voltage look like here? Elena? What does the voltage look like after it rectified, half-wave rectified? Right, half of the wave will show, right? Okay. So remember, in the explanation, you have to say that. In fact, we write this down because someone didn't do it yet. Right? Write down what, try to explain why we get this here, and then we will listen to Jacob soon. Write it down. Write down the explanation for how this happened. Huh? You're writing the question, say to explain. Read the question and answer that as a way answer. Malachi, did I get your parents' number? Eh? All right. Can I hear your explanation, please, Jacob? Yeah, Jacob, hurry up, please. What is the explanation? Why it says it went from full wave to half wave? What does it diode do? What does it diode do? So why it is only the positive fluid? Right, so during the positive direction, it is forward bias, and during the negative direction, it is reverse bias. So no current will flow during the negative part of it, right? I'll write it down, Jacob. No. All right, so remember, it conducts during the forward bias, which is the positive part of the cycle. I want to explain it, right? You have to write it. Right, so it conducts during the positive part of the cycle when it is forward bias. Right, and when it is reverse bias during the negative part of the cycle, and when it is reverse bias during the negative part of the cycle, it does not conduct. Let me see. Okay, let me see. Yeah. Right, copy down. Last part. Try the last part. Oh wait, well you have to do that. Dad. Let me see. Put the number. Oh, 2254532. Let me see. Wait in. Let me see. 225. Let me see. Show my number. Okay, don't worry. I must get. Right? What does the output look like? What does the output look like again? Jacob, what does the output look like again? What does the output across the load look like? Ariana, case has help Marvin. Right? So you have this. Right? Quick question. Will this be wrong? Suppose you had that. Would it be wrong? Huh? Based on your explanation, yes. But if you had said forward bias was when it's negative, then it could be right. Okay? Remember in our explanation, we said forward bias was positive, right? Okay? That's it. We have more. Have more, man. Sketches, please. Do a quick sketch. They gave you what? They gave you the peak value. They gave you the frequency. What do you have to do with the frequency? Raj? What do you have to do with the frequency? In order to plot it. Raj? What do you need? What do you need? They gave you a frequency, but you need something else in order to plot it. Huh? Close start time. What else? Malachi. Come outside. I want to talk to you. Kind of outside. Anybody remember? The question gave you a frequency, but in order to plot it, you need something. What is called that? Yes. Anybody? Anybody? What do we need? We need period, right? Period. Hurry up. Plot it quick. Plot it quick. Yes. Catch it quick. How many cycles we could probably fit in here? Maybe about two and something. All right, let's see how it went. The period is 2 seconds, right? So it moving up to 12, coming back down to minus 12, coming back up. Right? That is one cycle. Going up again, coming back down, coming back there. If you want, you can do an next one. Well, not the entire thing. So your cycle looks like that. You have the amplitude at 12, minus 12. So you need a period and your amplitude to plot, right? One more, I'll give you a small 5 minutes and then we take a look at the last thing, right? You know what? I could probably ask some people to explain things in magnets. Have enough people to pick one, right? Everybody will get a chance to explain something. Why on your phone? All right, let's go again. That was 2020, I think, right? Let's do one more. 2021. Do I have that here? Yeah. Yeah, I might finish before, but yes. 3:30 is the plan. That's the plan for sure, Dan. But is it? All right, let's try this one and see what it had, right? There's a magnet, so don't worry. That's Jan 2018. Write that down, please. Jan 2018 is magnets, right? We'll do that afterwards. I don't want to forget. All right, so that was Jan. One of the years that we was doing last, they had one. That's now. All right. Well, I'll give you a small break there, but let's start back one time, right? Yeah, that was the break. What one? But I ain't give all no work. Oh, sure. You know, come in the class. No break for you. You would just sit down there and do some work. Everybody else who was here on time can take a break. I don't know. I'm gonna start back now. The break up. Yeah. Take all the break. 2 minutes again. 2 minutes again, then we start. Jacob, let's sit down and now come. Sit down and do the work. Hurry up. Right, do some nuts and bacon. Let's start this one here one time, right? 2 earlier and 2 nuts and a break. Everybody else was here on time. If you leave it now, start it. Huh? Please, yeah? No, what you can do is you go outside, you get kicked outside. Right, take all the break and the other 4 we're eating KFC. Do this here. Yeah. It's up to you. You have exams for the next couple of weeks. Do this fast, right? After this, we start Magnus. Take a picture now. Jan 2013. All right, let's go. Jacob. How you know if your diode defective? Huh? What does the diode do? When you see your Solomon. Right? Ask the same question at least 3 or 4 times already. What does the diode do? Right. So how you know if it's not working? Right? So what's the circuit you can set up? Right? You need a circuit. You need a circuit to show that the diode possibly defective or not. Any ideas? Anybody? What we can do? Of course, the circuit must have a diode, right? What else we could put in it? AC current, very good, Jamion. And then a what? A what? Probably a battery might help. I mean, a bulb might help. Suppose that diode working properly. What's supposed to happen to that bulb? It will light and then what? Would it always light? Is that alternating supply? It'll be on and off, on and off, on and off. But suppose the diode not working. What will happen? It will stay off or probably stay on. Okay? So that simple circuit there could be used to determine if the diode is defective or not. That's okay? So all you have to say is set up as shown above and tell them what to expect. If the diode working, the bulb will flicker on and off. If the diode not working, it will stay on or stay off. What does the graph for the IV look like? Faith. What does the IV graph look like for diode? Right, well, yeah. Conducts in one direction alone. Right, nothing in the little or nothing in the negative part. Was it truth table for the NOT gate, Kayla? Was it truth table for the NOT gate? Truth table for the NOT gate. Yes, Malachi? All right. That is the truth table. What does it look like? Triangle with a little bubble in front, right? Next, what's the total resistance there, Kayla? Part 1. What's the total resistance there? Three of them in what? Series of parallel. Highest time resistance in series. Does it tilt table and make it right down? Add up all, right? Add up all. So the answer is what? 2 plus 6 plus 12 is? Do just write 20, yes? 20 ohms. You have 2 more parts again, finished up. Last 2 parts. Actually, you're trying to do 1 question, right, please? For the whole class, 1 question. All right, there we go. Magnets. I haven't seen transformers for a long while. I wonder if they make an adjustment. They just made the cuts on the syllabus. Right. Attilia. Attilia. Yes, Attilia. How do you find the resistance? What type of circuit is that? Parallel. How do you find resistance in parallel? 1 over R is equal to 1 over Attilia. 1 over 2 plus 1 over 6. How much is that? Attilia, how much is that? How much? 3/4. So what do you do to get the R value now? Flip it over. Good. Last part. Do the last part. Right? And I want the explanation, Carisha. Last part. Raj, you copy now all that there? Raj? You have all this? Raj, I feel all the questions in Magnus is yours, huh? In the back there and you're quiet. I hope you're writing down everything. All right, Papi. Right. Carisha. Ready? Someone ready? No rush. Yeah, Carisha. So last year for Christmas, Paula had to put together a set of bulbs to light her family Christmas tree. After much thought, she decided to put the strings together in series. Was it wise? Carisha, was it wise? That's an option. Yes or no? Pick one of them. Yes? It's a good option. Why do you think so? Why? Why you guessing for? Elena, help out. Was it wise? What's the problem with a series circuit? If one blow, all will be out. So it's better to connect it out parallel. Okay? So make a note of that. Parallel connections have independent control. Parallel connections have independent control. So it was a bad idea. Right? It was a bad decision because if one of the balls blow, all will be out. All right, last topic, magnets. Well, you can handle it now or while 5 minutes. Raj? Okay, good. All right. We have one more topic to do, that's magnets, right? During the topic, though, I'm going to be asking some questions. So hopefully you remember something. Okay, so we're doing magnetism and take a little break. We start back at 2:35. 10 minutes. I'll give you 10 minutes. 9 minutes now. Right? And we focus on magnets. Jacob, I'm not coming to look for, yeah? All right. Let me start magnets. Online, you all there? Adele, all there? All right. So magnetism, right? So the first thing we need to remember, we know a simple bar magnet has what? A simple bar magnet has positive, has north and south, right? Has north and south. Magnetic fields always what? Leave the north and go in towards the south. So magnetic fields always look like this. Leave the north, go towards the south, right? We also know that, oh, by the way, there is something called magnetic flux, right? Magnetic flux is the amount of field lines per unit area. So see, for example, here, and maybe here, which one has more field lines? The first one, right? So therefore, the magnetic flux is higher there. Okay? So the magnetic flux is the number of field lines per unit area. Right? We know that like poles repel, unlike attract. Same thing I gave you with the charges. Just do me a favor. Between these two bar magnets, draw the fields. Between these two bar magnets, draw the fields. Right? So your magnetic fields move from north to south. Attraction, south and south will not attract. But please remember to put the correct direction, right? The Lex in the middle there. Okay, so just some little things here to remember, right? Nice. Now we have something called current carrying conductors, right? Current carrying conductors are exactly as the name suggests. Conductors carry current. And around the current carrying conductor, there's a magnetic field as well. How do we figure out the magnetic field? Well, we use the right hand grip rule. So you have your right hand, right? And your thumbs, right? Your thumb will point in the direction of current, and those fingers will point in the direction of the magnetic field. Okay? So for example, let's take a look at the X. X means current going in. Take your thumb, point your thumb into your paper, and your fingers will point in a clockwise direction. Okay? Your fingers will point in a clockwise direction, right? So it means that the magnetic field is clockwise around current going in. Let's say you have current coming out now. If you have current coming out, right? If you have current coming out of the paper, your fingers will point in an anti-clockwise direction. That's okay? Right? So whenever you see the symbols, the X, just remember magnetic field around it is clockwise. When you see the dot with the little circle, the magnetic field around it is anti-clockwise. Nice. There is one that is very popular called the solenoid. You need to be able to get the magnetic field around the solenoid. Right? Real simple. You're using the right hand grip rule again, but here's what you're doing. In the right hand grip rule, it's a little bit different now. Right? Your thumb will point towards magnetic north, and your fingers will point in the direction of the current. Okay? So what you see? If you look here, this is positive, this is negative. Current going up, coming back down. You're seeing that? But if you look on the coil, right, Raj? Where are you looking? In the phone? If you look closely here, you will see current going down, going down, going down. You'll recognize the current going down. So you're taking your right hand and your fingers will be pointing downwards, right? And your thumb will naturally point towards North Pole. Check it there and see. Fingers coming down and your thumb pointing towards the left where the north is. You're seeing that? Pretty sure you're not doing that. Right? So your thumb pointing towards magnetic north. If there is north, here is south. And what do we know? Magnetic fields always leave the north and come into the south. Yeah, something wrong with these arrows on the end here. But they're actually coming in, right? Let's try our next one, because sometimes instead of doing the solenoid, we can do something like this. Currents coming out at the top, current going in at the bottom. Let's see if we can figure out the fields here. Current coming out at the top and the current going in at the bottom. Try it and see. Right? That's a solenoid, right? So you're using the same right hand. Current going in at the, coming out at the top and going in. I want you to tell me where your North Pole is. If it's on the right side or the left side. Okay? So therefore, watch it. So on the top, it's coming out. So your fingers will come out at the top and go in at the bottom. So your fingers following a pattern like that. And your thumb points towards the North Pole. Any class going on? Sit. No, sit down. Sit down. Actually, come down there. What?
On the YouTube and somebody said, there's no mining. Create and put a hand.
Which one? The same one? You sure it's not you?
So,
Somebody online?
purple key.
All right. Oh, I can't see those things. All right. So watch it over again, right? What does the dot mean again? The dot means current coming out. And the X means what? Current going in, right? So I'll try and draw a diagram here for you, right? You all seen it though? Right? So your fingers coming out at the top and your fingers curling back in at the bottom. So if you look here, your fingers going, oh, I could draw that, but I'm too good at the drawing. Oh, sorry. Right, let me see if I can fix up that. So your fingers might look something like this. Right, I won't be able to get the 3D part, but current coming out here and the current going in at the top. So you're taking your right hand and you're taking your fingers and you're letting your fingers come out at the top of the page and then the tip of your fingers going in at the bottom. And you will see that your right hand or your thumb pointing to the right. So if here is north, then here is south. Magnetic fields will always leave the north and go into the south. Leave the north, go into the south. That's okay? See the person online. Hey, check and see the person do it now. Hey, the person said okay. Then say anything. What's your name? Kimaya. Well, let me know if you understand, right? Are you okay with that? So what you all need to remember, you need to remember that dot means current coming out, X means current going in. Okay? And you're using the same right hand grip rule, right? But in a different way. Same right hand grip rule, but instead the fingers showing current direction, thumb points to the magnetic north. And this rule only works for this solenoid. All right? Now, we would have learned a little while ago, whenever you have two magnets together, they either attract or repel. So now, if I were to take, right, here's a next example, right? Here's the next example of what we're talking about. Now, if I were to take now a magnetic field, north to south, right? And I put a current carrying conductor inside it. Based on what we learned earlier, we should experience a force, right? Remember we said two north poles will repel, north and south attract, right? Same principle here. Because the current carrying conductor has a magnetic field and the magnet has a magnetic field, a force will be experienced. How are we going to figure out the force? Well, that's where Fleming's, why does that right hand? That's where Fleming's left hand rule comes in. That's the left hand, right? So, left hand rule. Thumb is the force, magnetic field is the first finger, and current is the middle finger. So see if we could use it here. Magnetic field moving from north to south. Current moving how? Out of the page or into the page? Out of the page. So therefore the force is what? Up or down? Upward. Right? The force is upward. Try it fast. Do it there. Do it on the TV. Relative to the TV. Magnetic field, north to south. Your middle finger has to come out of the TV So the thumb is pointing upwards. That's okay? Right. How we join that though? How are we going to draw? Yeah, going upwards, right? How we join the felines? The reason it going upwards is simple. All the felines building up underneath. And there's little or no felines on top. So if the majority of the felines underneath, what will happen? I will push it upwards. That's okay? And this left hand rule is used where? In the motor. All right? The left hand rule is also called the motor rule. Raj, you okay there? Raj hiding perfect behind Raj, but Raj, you enter? Right? So try this here for me. I given you a North Pole. I given you a South Pole. Tell me what direction the force is here. Try that, everybody. So you should be using the rule. Person answer. What direction are you gonna move? Left or right? Left, right, up or down? Work it out. So you should do that. Raj, I want to hear Raj answer. Same left hand, right? Is it going up, down, left, or right? Up, down, left. Can it move up or down? It can't move up or down, right? So the answer has to be left or right. Where you get, Raj? Left? Show me now. So you can one it half right again. Why? One die. The potato out. Okay, all right. Hello? Okay. All right. All right. Okay. Yeah, Raj, you got to the left. Show me how. Line it up now. Just yeah, do it relative to TV. Magnetic field is where? Magnetic field moves how? Raj, you wasn't paying attention in the back there. Magnetic fields always move from where? From north to south. So your first finger should be pointing downwards. Current coming in or out? X is in or out? Right? So your middle finger should be pointed into the TV. And your first finger still pointing down. So I'm looking kind of weird there. The first finger still not pointing. Come. Raj, you're not paying attention in the back there. So you watching the summary on your phone, you know? Huh? What? Right, left hand rule. So what is here? I'll use Raj, right? So left hand rule. We're trying to figure out the force. Okay? So these fingers saying just like that. So the first finger should be pointing downwards. Right? But the X is what? Current coming out. So this finger should be pointing outwards. This middle finger. Huh? X is in. Oh, sorry. X is in. Right? So what you did? Magnetic field going down, current going in. So the force is to the what? To the left? To the left, right? Right? So you guess right then. To the left. Right? So wait, hold on. Let me do it and draw it properly now, right? So the magnetic field moving down, current going in, so it's going towards my left. That's okay? Yeah? Right, one for the road. Hurry up. Just one more. Well, one more to finish this. Not for the road. Sorry. Check this one out here. Up or down? Up or down? Up or down? Right? So north to south, that means what? That means, so therefore, based on the diagram, it's looking like down. Okay, nice. So this leads us to the why is the left hand but the right hand not there? All right, that leads us to the motto, right? I will have to draw it. I'm not seeing the motto here. Something missing, boy. Yeah, boy. All right, I will draw the motto and just run through how it works, right? So your motto is made up of a magnet, right? Magnet. Then you have a rectangular coil connected to a supply. And then you have rings. What do you call these rings again? What do you call those rings again? No, you just call them slip rings, right? Right? Those are called, that's not, those are called split rings, ones that split in half. Right? Those are split rings. Right? So if you look here, watch the diagram first. Current moving this way, coming up here. Current, let's say here's A, B, C, D. Current going up A, B, down C, D. Okay? So the current is moving from A to B, down C to D. So we have to figure out what direction the force will be. Fleming's left-hand rule. Magnetic field, north to south. Current going up AB. So the force here will be downwards. Next side, north to south. Current going from C to D, the force will be upwards. So it will cause it to turn in a anti-clockwise direction, right? What allows it to turn continuously? These split rings, sorry. Those split rings allow current to flow in the same direction and allows it to turn in the same direction. Anybody remember what has happened when it's vertical? Right? When the coil is vertical, inertia allows it to overcome the stationary position and continuously move in an anti-clockwise direction. All right? I gave you all the steps for the write-up, right? I'll give you the steps again for the write-up. What's the difference between the motor and generator? The motor takes electrical energy and gives you mechanical energy. Right? So you're taking energy and the energy allowing it to turn. But what does a generator do? Right? The generator will take the mechanical energy and give you the electrical. So there is no battery in a generator. You have to turn the motor and the motor will turn. And because of two laws, it will produce a voltage. What are the laws? Faraday and Lenz's. Very good. What did Faraday say? Faraday said that the faster the conductor cuts the P lines, so imagine you have P lines, the faster the conductor cuts this, the bigger is the voltage. And Lenz said that the direction always opposes motion. All right. So the direction of the induced EMF is such that it will always oppose the motion. Right? These are the laws here. So for example, Faraday said the faster this magnet moving in and out, the bigger is the voltage. Lenz said that if a north pole going in, a north pole will be formed here to oppose the motion. So if a north pole is formed here, south is here, and we can figure out current going in a anti-clockwise direction. Please learn that the current and the galvanometer moves in the same direction. So the current going left to right, the galvanometer moving left to right. Well, will be on the right side. If the current going the next way, the galvanometer arrow will be on the opposite side. That's okay? So please remember that. Remember, once you figure out where the north pole on the solenoid is, come back and use the right-hand rule. And you can figure out the current direction. Okay? The right-hand grip rule. Right? And last thing, transformer. Transformer uses electromagnetic induction, and it has the ability of taking a voltage in the primary and inducing a voltage on the secondary. Okay? And this here is a transformer formula. But this formula only applies if the transformer is ideal. All right? Okay, so that's a summary on magnets. There aren't many questions, so let's go and do what's the year said again? 2018. Let's take a look at Jan 2018. Right, you'll notice in the older years, we'll have a lot more, right? There's one in 19 or something, but I don't have that one here. Go ahead. Do that fast. Right? Current directed into. Hurry up. Currents directed into. Draw the magnetic field. Quick. Draw the magnetic field. In is what? X or dot? In is X. So draw the X and the magnetic field around it. Hurry up. Oh yeah. So draw the current going in. You have to draw the pole in. Where's it? No, don't draw it in there yet. Don't draw it in there yet. Part 1 is to see, draw it by itself. Part 2 is when you put it inside. Right? Knock it on a 7 while we lead us in. All right. Right. Remember, the first part has nothing to do with that. Huh? The first part is just to draw the field lines around there. What's the field lines around there? X is what? Clockwise or anti-clockwise? Varaj? Clockwise or anti-clockwise? Clockwise? Yeah, man, you get through, man. Good job, Raj. Now, in the next part is when you put them together. So you have to work out what will happen when a conductor goes into a magnetic field, Shivanan. It'll experience a... Say, excuse me now, why? Yeah, Shivanan. When a current carrying conductor goes in a magnetic field, it experiences a what? A change in what? A force, right? So you have to work out the force and then draw the field lines. Hurry up. Quick, likely. Right. Carisha, up or down? What direction is the force? Sorry, I wasn't listening. Sorry. Carisha, what direction is the force? Shimana, how you get that? What's the rule they use? How you use the left hand rule? Somehow you use the left hand rule. Huh? How you get it down? The force is the thumb. Unless we changing up, you doing your own thing then. Right? So basically, the current going in, the magnetic field north to south, and the force is down, right? But they want you to draw the field, magnetic fields, right? So remember, it will build up on top. And it will have less underneath, pushing it downwards. All right, Carisha? All right. Let's see all the message in here. All the message in here. Now it's time to explain the motto. The reason I like this question so much, it gives you the guidelines to explain it. Right? So remember, if it's going down, all the field lines on top, pushing it down. Hello? Give me a while now, finishing this class. Okay. Now. Sorry there. Right. Before we go into explaining the what is this, a motor or generator? A motor, Carisha. Carisha said motor. Why Carisha? Because you have the split ring. Okay. And you have a supply as well. What is called X? What is called the X? The split rings, right? Yeah. It's called the split rings. Okay, nice. So here's what they want. Explain what happens when the switch is closed, and they tell you exactly what they want. What is the direction of current? Write it down. Write down the steps. Remember, I told you I'm going to give you the steps. These are the steps. Write down the direction of current. Number 2, write down the forces applied. Number 3, write down the rules applied. Number 4, excuse it right there. I just reading it out, sir. Okay. Okay. Right? And next one, direction of rotation. And last one, how continuous rotation is achieved. So I want to write down those, how much? 5, 1, 2, 3, 4, 5. Write down the 5 points and try to answer it one at a time. All right, I'll go back to the diagram now. Write down the 5 points and let's do it one by one. I'm giving you a little time. Write down all 5, so we don't have to answer all. All you have to do is the diagram is label it. Right? I'll listen to a few examples and then we're done. If you name of an A in it, you will be reading. It don't matter. Don't matter. Avocado. Hawaii. All right. So those are the 5 things, and that's what I want you to learn, right? Don't memorize the passage or don't memorize an explanation on it. Try to make sure you can do it when exam come, right? So I'm going back to the diagram. All your diagram missing is a labeling. Just label it. A, B, C, D. Label the coil. All right. Oh, wait, you have a labeling already. Right? Do your thing. Answer each one. And then we are going to do our explanation. Answer it one by one. Point 4. Right, time to reach out. Come on, put it direction. Tell us everything. Let's figure the current direction. Well, I know, but you have to figure out. All right. When you close this circuit, right? Which side is positive, which side is negative? Huh? Look at the battery down there. Hmm? You're seeing that? Current is going to go up, go to DC, BA, and then come back down. Right? Use that now to figure out everything else. So, answer number one. Current is flowing from D to C to B to A. Right? So number one, do the exact same thing in the exact same order. Right. So current moving from D to C to B to A. What's number two? Huh? No. What they ask? The force? Right. So the force exerted, left hand rule, the force exerted on DC is downward. The force exerted on BA is upward. But. It will turn how? Clockwise or anti-clockwise? It will turn in a clockwise direction. What's the law you use? Fleming's left hand rule. Faraday. That's a generator. That's Faraday's and lenses. That's something else. Right? That's similar. This is pretty much so. That's the generator. Right? So it looks something like that. That's okay? And what's the last part? How does it maintain continuous motion? Huh? One, when it's in the vertical position, inertia allows it to continue to move, and the split rings allow current to flow in the coil in the same direction all the time. Right? So therefore, it will experience the same force all the time. You okay with that? So you have to learn to answer each one. Right? All right. So that brings us to the end of all topics. We didn't get